Welcome to the Deep Dive, where we unpack the knowledge you're seeking, tailored just for you, the learner. You've sent us down a really interesting path today with material tackling mathematics. It's a subject, isn't it, that people find either incredibly powerful or, well, utterly baffling.
It really is. You get that split,
Yeah.
yeah. On one side, it's this beautiful, powerful logic machine. On the other, it's that when will I ever use this feeling? But underneath all that, there's a way of thinking that's just so valuable.
Totally agree. And that's really our mission for this deep dive. You've shared these excerpts from How to Think Like a Mathematician, and we're going to pull out those core insights, those aha moments, to help you get beyond just doing the math problems to actually thinking like a mathematician.
Right. Think of it as a personalized guide through that undergraduate math companion you sent.
Exactly. So
Mhm.
where do we even start to unpack this way of thinking?
Well, the book kicks off by sort of reframing how we even learn math, starting right with how we read it. The big idea. Forget reading it straight through like a novel, page one to the end.
Oh, that's immediately a relief. Yeah, the idea you have to absorb every single detail in order,
Yeah.
that can feel pretty overwhelming.
Exactly. So the first kind of liberating idea is it's okay to dip in and out. Take what you need, what's relevant right now.
Makes sense. More strategic.
Precisely. The author lays out this simple system, though it's not rigid. Skim first. Get the lay of the land. Ask questions, what are you curious about? Then, read carefully. Be active. This is key. Check the text, do the exercises, and finally, reflect.
So it's a cycle, not just a list you tick off in order.
Not at all. You might skim a proof, get stuck, ask yourself why, then zoom in and read that part really carefully. Maybe try working it out yourself before reading their explanation.
Right, right. It's like having a conversation with the book, not just downloading information. And that active part, you can't just skim the symbols, can you?
No way. And a really good tip the book gives is to look for theorems or formulas you can actually calculate with. Get your hands dirty. Seeing the abstract stuff produce a concrete number, that can really make it click.
Yeah, that bridge between theory and actually doing something with it, that's solidifies things. Okay, so early on, the material dives into some really fundamental notation, set theory stuff.
The subtle but super important difference between is an element of and is a subset of, and the concept of the empty set, the set with nothing in it.
Right. Seems almost trivial, doesn't it? A set with nothing.
It does. But it's foundational, as the book points out. Understanding it, like the difference between Eva Ho and the empty set versus a set containing the empty set. That clarifies a lot.
Ah, okay. That set has one element, even if that element is, well, nothingness.
Interesting. Okay, so then the focus shifts, and this is really key to how we write mathematics.
Yes, and the big takeaway here isn't just about communicating to others. The act of writing clearly actually forces you to understand the material better. It crystallizes your own thoughts.
So how do we do that? What's the advice?
It sounds almost too simple, but write in simple, correctly punctuated sentences.
Simple sentences. Okay. But math isn't just words, it's symbols. Exactly. But the symbols have to live inside those sentences. The book gives this great example of a student writing something like 0 or 1, no solutions, empty set.
Yeah, I saw that. You kind of get what they mean, but
But it's not a sentence, it's just fragments. The symbols, the concepts they represent, need to be woven into grammatically correct statements. Since 0, 1 is impossible, there are no solutions. The solution set is the empty set. Something like that.
makes sense. And the punctuation matters even with the math symbols embedded in the sentence.
Absolutely. Commas, periods, they guide the reader, they structure the logic. The book also warns against super complicated sentences with lots of knots. Keep it clear, keep it simple.
Clarity's king. Okay.
And explain your reasoning. Don't just jump from step to step. Use connecting phrases because, since,
Yeah.
applying theorem 3.1. Give that running commentary. It shows your logic.
Like showing your work, but narrating it.
Yeah.
Got it. Any specific notation pitfalls?
A few common ones. Always use then in an if-then statement. Don't leave it implied. It avoids ambiguity.
Okay, if A, then B, explicit.
Right. And be careful with words like formula. Not every jumble of symbols is a formula. Things like 5a plus 2b are expressions or terms. A formula usually involves an equal sign, like an equation.
Ah, good distinction.
And the big one, the implication arrow. It implies that. It connects statements. You don't use it like an equal sign, and you definitely don't start a sentence with it.
Right. That's a common mistake, isn't it? Seeing it used like a shorthand for, so the next step is...
Exactly. If you're tempted, just write out, this implies that, or therefore.
Mm.
And finally, always define your symbols. Even if you think is obvious, just state what it represents. Clarity, clarity, clarity.
Okay, so clear writing is fundamental, both for yourself and others. Makes sense. From there, we move into problem-solving strategies. Polya's famous plan.
Yep, George Polya's four-point plan, still incredibly relevant. The steps are 1. Understand the problem. 2. Devise a plan. 3. Carry out the plan. 4. Look back.
Simple steps, but the book digs into what they mean for math, right? Starting with understanding the problem.
hmm That means really pinning down the hypothesis. What are you given? What are the assumptions? And the conclusion, what do you need to find or prove? Getting that crystal clear up front is crucial.
Seems like good advice for any problem, really.
Totally. Then, devising a plan. The book talks about lots of strategies here. One great one is working backwards and forwards. Start from the goal and think, what would I need just before this? And also start from what you know and see where it leads.
Okay, attacking it from both ends.
But big caution here. When you write up the final proof or solution, you can't assume the thing you're trying to prove. That's fine for exploration, but not the finished product.
Right. The example of the zeros at the end of 100 factorial really shows that. You have to figure out how zeros are made, factors of 5 and 2, and count them, not just assume the answer and work back.
Exactly. Other strategies mentioned? Break big problems into smaller pieces. Find the right level should you use a big theorem here, or go back to basic definitions.
And giving things names. Translating the problem into math language.
Yes. Assigning variables, using notation, that act of translation is often half the battle. And, like we said with writing, consciously choosing your proof method. But that last step, looking back, is vital too, isn't it?
Yeah, getting the answer isn't the finish line.
Right. Does the answer even make sense? Is it ridiculously big or small? The book has funny examples, a car going faster than light, the sun being 5 miles away. You need those sanity checks.
Yeah, basic reality checks.
And other checks too. Do the angles in your triangle add up? Does the parity even work out? Also, can you find another way to solve it? And crucially, what did you learn from solving this? Reflecting is key for growth.
Makes sense. Okay, shifting gears a bit. The deep dive goes into the absolute bedrock logical thinking, starting with statements and implications.
Yeah, because at its heart, math is about proving statements are true or false. And a mathematical statement has to be one or the other, definitively. No ambiguity.
Okay, that leads to the basic logical operator. And, or, not.
The book uses truth tables, which are helpful. Key thing with or. In logic, it's usually inclusive. A or B is true. If A is true or B is true or both are true, that's sometimes different from everyday English or.
Right, like you can have soup or salad usually means one, not both.
Exactly. We also get equivalent statements. Same truth table means logically the same. And De Morgan's laws for negating and or, then the big one, implications. If A, then B, or A, B.
And most math theorems can be phrased this way.
Pretty much, yeah, even if it's disguised. Like all squares are rectangles is really, if X is a square, then X is a rectangle. The book also notes that B of A means the same as if A, then B.
Okay, and negating an implication, that's important. It's not another if-then.
No. The negation of if A, then B is A and not B. That's a really common point of confusion.
Got it. And that leads to inverse and contrapositive.
Right. Inverse is if not A, then not B. Contrapositive is if not B, then not A. The crucial thing, shown with examples like the odd squared one or the Winston Churchill one, is that an implication and its contrapositive are logically equivalent. If one is true, the other must be true.
But the implication and its inverse aren't necessarily linked like that.
Correct. An implication can be true while its inverse is false and vice versa.
That equivalence with the contrapositive feels like a really useful tool for proofs later on.
It absolutely is. Then there's the converse. If B, then A. Again, totally different logically from the original if A, then B. And finally, if and only if means the implication works both ways. A implies B and B implies A. They're logically equivalent.
Okay, that covers the basic logical structure. Then we get quantifiers for all, and there exists.
The universal quantifier and the existential quantifier there exists. These let us turn like open sentences with variables into actual statements that are true or false.
Right, like x squared 4 isn't true or false until you quantify x.
Exactly. X in integers, x in sequus 4 is false. But x in integers such that x success tree is true, x2 or xc2. And notice the such that it's often added when reading statements to make them flow better.
Okay, and combining them. The order matters hugely.
Critically, x for every x there's a y is completely different from ax. There's a y that works for every x. The book gives a good example with relationships to show this. And negating quantified statements involves flipping the quantifier, becomes X, and negating the sentence inside.
Got it. Flip the quantifier, negate the rest. Seems logical. The text then really emphasizes examples and counterexamples.
Oh, hugely important. Examples help you wrap your head around definitions, test if you understand a statement, remember things, explain things to others. They're vital.
And not just using the book's examples, but making your own. And even reversing the process, like designing a function to have certain properties.
Yes, that act of creation is where deep learning happens. Trying to build your own example forces you to really grapple with the definition. And thinking about non-examples, things that just miss the definition, is also great for understanding the boundaries.
Like understanding continuity by looking at a function that's discontinuous.
Precisely. And of course, counterexamples. That one case that shows a general statement is false. Finding those is a key mathematical skill.
Okay, so active engagement with examples is crucial. Then we get to the building blocks. Definitions, theorems, proofs.
Right. Clarifying the terms. A conjecture is something believed true but unproven. An axiom is a starting assumption. A theorem is a proven statement. Lemma, proposition, corollary are usually smaller or related results.
And it mentions mathematicians sometimes use these terms a bit loosely, like with Fermat's last theorem being called a theorem long before it was actually proved.
Yeah, historically things can be a bit fuzzy. A really key point when you meet a definition is to ask, do things that fit this definition actually exist? And if so, are they unique?
Like, even numbers exist. Odd numbers exist. Are there infinitely many twin primes? We don't know for sure if they exist infinitely. Existence isn't guaranteed.
Exactly. So when learning a definition, find standard examples, find non-examples, try to build new things from the definition. When analyzing a theorem, what are the assumptions? What's the conclusion? What if you change the assumptions? How does it relate to other theorems? Can you draw a picture? Does it work for